set that you have cleaned and you feed it into the system, the next thing you need to do is to focus on which of the performance metrics could help you to be able to understand the patterns that your data set has captured. So basically, today we are going to focus on this part of the machine learning pipeline. So we try to evaluate what the algorithm have learned and which of the matrices we're supposed to use to be able to understand if what the algorithm have learned are not noise, but at the end of the day, they are actually patterns. So we said different models will require different matrices for evaluation. So when we talk about this, it's just like consider a chef in a restaurant or in a hotel that needs to cook. Most of the time, they have to mix different recipes. They have to do it carefully, not just you poured salt, you poured it. No, by the time you serve your customers, if you don't take time to make sure that the recipe the end product you're giving them is not messed up, else you will drive the customers away and they won't have to come to your restaurants to patronize you on what you're cooking. So the same way as a data scientist or an AI engineer or a software engineer and so on, when you are developing your machine learning AI models, you have to make sure that the metrics you use to evaluate the model are the right ones and they are capturing the right pattern in your data set. Now, if you remember from the beginning of this class, we talk about the classification problem and also the regression problem. And each of those problems have their own matrices that you could use to evaluate their performances. So remember we said the classification has to do with categories and the regression has to do with continuous variable. So based on this, you could clearly see that they are not the same, although they could all be under the umbrella of supervised learning, machine learning. But that doesn't mean that they are the same, we evaluate them in the same way. No. So the classification example we talked about last time, we talked about the email spam, and then we also talk about the disease diagnosis in the case of cancer and all that. Then in the case of regression, we talk about the housing price problem. There is also the temperature predicting. For example, uh, you want to know what's the atmospheric pressure, for example. Pressure is not something that you can easily quantify it high because it changes, it very continuous on a continuous scale. So you have to make sure that you're measuring it using the right instrument. But when you want to know what is going to be the probability it's going to rain tomorrow, that's already a classification problem. That's not a regression problem. And we also, if you remember, we talked about in our last class the unsupervised problem. So each task required a specific evaluation metric to assess this performance effectively. So in the case of regression, you have to make sure that you're going to be using the right performance. So, but however, we're going to focus today, we're going to focus more on the classification problem. Although that doesn't mean we not talk about the regression problem, but I think much of our attention will be focused here because the classification problem seems to be very, very common. And because most of the time, when it has to do with qualitative data set, you're likely going to be using classifications to be able to understand the outcome or target variable. But most of the time, the quantitative, that's where you're likely going to be using the regression approach to be able to understand the problem. But most of the time, you discover that qualitative has to do more with what we do almost in our everyday lives. So we really get to see those things. But again, it depends on the areas you are much more interested in. But most of the time, the classification seems to be much more prevalent in our society. So the first thing, in order for you to understand uh, this classification and matrices, you need to understand this table. Now, this table that you're looking at, is called the confusion matrix table. Now, the confusion matrix table is a table that is able to split or categorize the predictions that we have made based on the comparison with the actual instances that we guess right or wrong. So, when we talk about, for example, the predictive positive, it talks about the positive that the instance we predict right based on the fact that they were actually right. So that's why you see that we said predicted positive and we have actual positive. So if we have in the target variable, we have the fact that this person is going. We have 10 cancerous patient, and then we have 20 non cancerous cancer patient, and then we split. We train our algorithm. We do the testing because remember in the testing set we do have the label, but we will always withhold it and then we compare it with the prediction that we have made on that testing set. So you could imagine if we have 10 of these patients that have cancer, and then we make our prediction, and then let's say in our model we identify 9 of them or 8 of them. So it means that when we come back to compare, we say, oh, we get 8 right. So it means that it is like 8 over 10. So it means the 8 people you guess right is your true positive. However, the remaining 2 people that you did not guess right, they because it means that your model actually said they don't have cancer, even though they have cancer. So that's kind of situation, you discover that they are false positive. So it's more like what we could say a false alarm. So this this ones actually did happen. They did have the cancer, but it said no, they don't have the cancer. So that actual positive, because that's a negative case. So it was supposed to say they do not have cancer, but now it said they have cancer, even though they do not, they did have the cancer. So that's the sort of a type 1 error. We say type 1 error because um the reason is that type 1 error itself is when we try to, so when we state the hypothesis and then we reject the null hypothesis when we are supposed to reject it at a certain confidence interval, then we say it is a type 1 error, let's say 95% confidence interval. So that sort of error is not a big issue, although it depends on the cases. But when is a problem to the system is when they don't have the cancer, but the system said they did have cancer. That's the algorithm now saying, no, they have the cancer, even though they do not have the cancer. So that kind of situation, this is a false negative. So it is a type 2 error. And if you know type 1 and type 2 errors, we usually use beta and alpha for type 1 error, beta for type 2 error. That's kind of an error. It's a big issue. You could imagine in the case of um, medicine or biomedical sciences, where this person don't have cancer, and then the machine predicted and said the person did have cancer. Okay, let's even leave cancer. Let's use things like HIV/AIDS. The person do run a test on HIV and then discovered the person do not have HIV, but the system said this person have HIV. Do you know that could trigger the person to even go and commit? There are people that cannot handle these things. They could see it as an end of life, and they could even go and commit suicide or something. And that is actually a very big problem. So it's a very big problem. So again, it depends on what is much more important for you. For example, when we during COVID-19, the beginning of the pandemic, there was this contact tracing apps that that came in. I think some were using Bluetooth and all that. where once they detect someone that had the COVID within certain range of meter or something, it start bleeping in some cases. So the thing then was that something like COVID, you could imagine if the person had the COVID and then the system come and say, no, that person do not have uh, COVID. And then you know how COVID spread that period. It was quite something new that we don't even know anything about it. And even our system was not used to it. It's not like now that our systems must have developed antibodies that could, even when you contact it, you don't really have issues with it. That was a new disease. So you could imagine the issues it will be when you detect false positive. So in that case of like COVID, is a very big issue because the system is leaving people that did have the virus, and then they are going free, and going free they will infect other people. So you see that's a very big issue. But now when you now go back to maybe something like malaria also, you know, these are maybe not. Anyway, those days, malaria was a life-threatening disease, especially to somebody from the Western descent that do not have any form of antibodies against malaria is an issue. But for us, for someone coming from West Africa or Nigeria, you already know, like, even if somebody said, "Oh, I have malaria," you like, "Oh, it's fine. You just go get drug and take and all that." So in that kind of a situation, maybe the person did have malaria, but the system say the person doesn't have malaria. It's not really going to be a big issue because you know that okay, this disease is not even going to be spread. It has to be from the plasmodium parasite, which is in that mosquito, takes it to infect another person. So again, it depends on the issue you have at hand. So again, like I said, false positive cost could be very, very big, and also false negative cost could be. So it depends on the issue. But now, the true negative is when that person do not have the disease, for example, and your model actually predicted that person and say the person do not have the disease. That's beautiful. That actually shows your model is doing well. It was able to detect people. But like I said, the false negative will be when that person do not have the disease, but it said he did have the disease. So now let's look at each of these metrics, what they are measuring. So the accuracy is that metrics that measures the overall correctness of the model, or the percentages that the model actually got right. Now, let's look at what the accuracy means. So if, in other words, if you're putting it as a formula, you're going to express it as the true positive plus the true negative all over the total population. So the accuracy is simply this one and this one divided by this. So all the population, meaning true positive, true false negative, false positive, true negative, that will be what makes up this all population here. Then, but in the case of the error rate or the misclassification rate is now going to be the false positive that you have plus the false negative you have plus the false positive divided by the total population. That gives you now the error of the models that you have missed out. Okay, so you could actually see that the error rate is basically those ones that you couldn't pick up in the system. Then when you now talk about precision, now precision, like the name connotes, it's just basically telling you how many of the actual positives were correctly predicted right. So that's what the precision is focusing. Was your model able to really identify these patients that actually have the disease? So it means that your precision is going to be what? The true positives here and the number of the true positive plus the false positive. So remember, it's focusing on on only the positives. Okay, so if it's focusing on only the positive, it makes sense for you to look at the ones that you missed out with the ones you get right. So the precision is focused on the true positive plus the predicted positive, that's TP plus FP. So in other words, you are going to be talking about everything is centered on this place here. Your focus is just going to be here. So the TP is going to be this one, which is the actual positive you have, and then the FP is going to be this one here. I think they're not supposed to say predicted positive because there is the actual positive TP, but that's fine. So what we are trying to say here is that the TP plus the FP, which is this one and this one, then divided by the true positives gives you the precision score. Then we also have the sensitivity. Okay, so we have the sensitivity score. Now the sensitivity score actually focus on how many we also call the sensitivity recall. Sorry, so I think the broad name should be recall. It talks about the measures of how many actual positives were predicted correctly. So again, it's still on the positive because the positive is also very important. Like I told you guys that most of the time, the positive is a rare occurrence. It's not always the dominant you find out in your data set. Sometimes it will be very, very few of them that are positive. So such kind of situation, you have to be very, very careful so you don't miss out these occurrences that are quite important. So the sensitivity will be the true positive plus the actual positive, that FP plus FN. Now, remember FN is this one. So the recall will be focused on this row. Remember, precision is focused on this row here, while the recall focus on this column. So it's going to be the true positive plus false negative, which are this one here, divided by the true positive. The true positive divided by the sum total of these two, which is also a very important one. However, another very important metric that I like using it a lot, and shortly I'm going to tell you why I prefer using it to most of the other metrics, is the F1 score. The F1 score is simply the harmonic mean of the precision and the recall. So what that means is that it is going to be 2 times. Now, this whole thing is just that we don't really have a board, and I think I'll try to see in the subsequent classes to get a whiteboard so I could be able to show you how we could derive some of these things. But if you know your equations very well, it starts with 1 divided by the recall plus 1 divided by the precision. Now, when you have to add these ones, what you need to do is to take the LCM of the board. So if you are taking the LCM of the board, it means you are going to have this times the precision, then all over, you now divide these other ones so they go up. And when they go up, you again use somersault it. So, but again, I don't want to bother you much with the mathematics, but that's how you derive the recall. It's 1 all over the recall plus the precision, and then you turn it over. So, but again, the final thing you should know is that it is 2 times the recall times the precision all over the recall plus the precision. So the reason, one of the things is that when you looked at it very well, you could see clearly that the F1 score has both the recall and the precision, which makes a lot of sense because the precision is this row while the recall is this column. So they is very, very important if you want to gauge how your model is really doing well. The F1 score is one matrix that you should pay a lot of attention to. Now, I will talk about the confusion matrix, which is still this one I showed you. But why the confusion matrix is very, very important is because the confusion matrix actually help us to visualize at one go the performance of our model. It helps us to know, for example, the number of total true positive we have, the false positive we have. So most of the time, when I have a confusion matrix, the first thing I looked is the diagonals. I just looked at the true positive and the true negative. Once I see that, oh, these ones are doing well, I could be able to know in my head that, oh, the model is actually trying. But suppose I now do the model and I discover everything is on this actual positive. It means that your model couldn't detect any reasonable thing other than noise. So, it could really help you by just looking at the confusion matrix. It will actually see if you are underfitting your model or you are overfitting your model. So this confusion matrix is a very, very important tool that you will use and you will need it as we keep going. And I'm going to tell you really why you need it. So remember, I have two things that I want to tell you about. One of it is why I prefer the F1 score. The second one is the confusion matrix. However, I'm going to tell you a bit in the next slide. So let's look at in great detail how the accuracy score matrix works. So remember we have let's look at the email spam issue that we talked about in our previous slide. If you looked at the number of emails that comes into your inbox that were classified as spams, let's say you have 37 of them that came in, or let's say there are 45 of them that came into your email, but 37 was correctly classified as spam mails. So the precision, like I said, is going to be the 37s divided by the total emails that came into your inbox. So the same way we remember what we said: the true positive plus the true negative, the true positive plus the true negative plus the false positive plus the false negative. So all the predictions, that you have, or all the things that came in divided by the ones that you correctly identify. So in other words, it's looking like it's this guys here, the diagonal matrix here, against every other thing in the confusion matrix. So it is very, very important to know when can you use this accuracy. I would advise you to use it when the target variable have a balanced class. It means both the number of positive instance and negative instances are the same. So if you have them, or you notice that the imbalances is not that skewed much to one class, then I would advise you that, okay, go ahead and use the accuracy, because the accuracy begins to have problems when you have imbalanced classification problem. When you have imbalanced classification problem, you're likely going to see that the dominant class is going to overshadow the negative or the underrepresented class. And most of the time, like I said, the class of interest or the positive class is mostly rare occurrences. It's things that doesn't really occur frequent. Imagine if you are trying to look for skin cancer in 1,000 women, and then in this skin cancer that you're trying to screen, let's say you are much more interesting in looking at skin cancer that occurs in dark skin. Now, probably in the 1,000 women that you screened, in that dark skin, the algorithm may not really maybe do, maybe the dark women you identify were very few. Probably you picked 50 or 100 in 1,000. That's heavily imbalanced classification problem. So because it's heavily imbalanced, the model will perform based on what it frequently see. So if it sees more of the negative instance, it's going to do the same thing when you extend it to the testing set. So that way you will be getting the dominant class doing very well, but the underrepresented class is likely going to do very poor. So you have to make sure that the class of interest It's not discriminated. So you have to make sure you looked into the metrics to say, oh, is this accuracy actually picking up that class 2 that is not represented? Now, when we talk about it, now try to visualize what it means to be accurate and precise. Now, you could see when we talk about the model doing very well, it means its ability to be able to accept, to detect this point very well. For example, in the case of this model, we will say it's very precise because we have 37 over 45, which will have above 90 when we're looking at the accuracy score. That's quite a precise model. But there are situations where we will have the model is precise but it's not accurate. And this is what it means. It means we could be able to detect more of this. Remember the table I showed you earlier on, which is this one. So the model is having more within this point, and it's not picking anything within this point here, which is not right. It means that something is really, really wrong. So you have that it's going to be looking like this when you open it. It means that most times the console that you're looking, it's really leaving the core parts, which is where you're supposed to have everything detecting. And these are curves, okay? These are curves. So when you're looking at them in the number line, they'll look something like a normal distribution and all that. But when we're talking about, trying to visualize them in form of what we call, I'm trying to remember the names that we did this in mathematics, but I think one of those algebras that we did those days. So you discover that the precision is not picking it. It's supposed to be mostly concentrated around the core parts here. Now there is a situation where you have it's just picking noise. It's neither accurate nor precise. It means you are likely picking everything that has to do with the most represented class. And that's what really happened most of the time when you have imbalances or when the target set is not even capturing enough signals to be able to, or it's supposed to even be because the target variable is an approximation of the independent variables. So if the independent variables are not explaining the variability, it means that it's going to be a problem. It means the target set and the independent variable themselves are not conforming. They are not, matching up. They don't connect to each other, or they are not cross-talking in some way. So you have to reevaluate such problem and see if it actually fits in what you're doing. Then there is a situation where you have the model is accurate, but it's not precise. So most of the time, you can see the concentration is largely here and it's kind of out of the box. So these are some of the kind of scenarios that you'll be confronted with as you explore machine learning practical problems. You're going to see where the problem is precise and accurate. And that would be like a very good one. You'll be happy, oh, you have cooked a very nice meal. And then there is a situation where there is lots of salt and then the whole food is not, that's a very big problem. So it's precise. No. I think the salt is fine, but the recipes were badly mixed. That should be the proper example. So that kind of situation is precise but not accurate. So but then there are situations where you have the both of them, they are not even they are not adding up at all. I remember a movie I watched some time back where the lady was asked to cook an indomie, and then instead of her to follow the normal procedure and all that, what she did was to put salt, she mixed all the recipes, and then she didn't on the gas to put the indomie. She just do the whole thing and then bring it and give the person like that. Say, and I was like, is that how you cook? And she said, I've never cooked. And so the person was so disappointed because at the end of the day, this is not how. So that kind of situation is not accurate, it's not precise. The person didn't get it. But then there are situations where it's accurate, but it's still not precise. So you have to make sure you take note of the accuracy precision trade-off when you are considering the metrics to use. Now let's zoom into this precision recall thing. Now, like we said, the precision, when you look at the confusion matrix, is basically you're talking about the rule. So the true positive divided by the true positive plus the false positive. So in that kind of situation, if you have, let's say, total of 6 emails that came into the inbox of that person, now you were able to identify or correctly match these three. So let's say 6 email came and they were spams. Out of these 6 emails that came and they were spam, your model said 3 of them are actually spams. The other 3 are not. So you see, the model is average in this case because I identified just 3 of them. But now when you are looking at the precision, it means you divide the 3 by the 6 email that came into the inbox. Then in the case of recall, the recall in this case is going to say how many of the true positives you were able to actually predict them that they were right and they were actually true. They were this true positive. It was only 3. So in this case, out of the 6 that came, it was only 3 that your model was able to identify that were correctly spams, despite that they were actually spams. So that case, it will be 3 divided by 3. So you see the differences. So in the case of precision, you will look at the 6 of the emails that hits of the messages that hit your mail, and the 6 of them are actually that spams. Then you add up, and then in the other case, you have to just focus on the actual ones that came in that were actually predicted to be spam mails. So increasing the precision may lower the recall and vice versa. Yeah, this is one thing that a data scientist struggle with a lot because you have to always be tweaking your model. You check the precision, you check the recall. And then again, another thing will come up. What is it that your hypothesis is actually interested in? Is your hypothesis much more interested in precision or is interested more in recall? So you have to put all this together before you actually choose the metrics that you're going to settle with. So one of the niceness or one of the best thing about the precision is that it's very, very valuable when you're dealing with imbalanced data or classification problem. Because in this case, you want to know the false positives that you are not that you are missing out. Because the cost of missing this false positive is very, very great. So you have to ensure that you are identifying them and you are now going to put your model into scrutiny and say, why am I really missing this, guys? What's actually the problem? And then you begin to, interrogate your model. So precision is valuable for imbalanced data and when false positives are costly. So like I told you guys about the COVID case, you cannot just allow the person that had the COVID as of 2020 when we were new to just be going about. That's why then you see that the government will have to do lots of contact tracing and everybody that the person come in contact with will be put into isolation so they could contain the spread of the disease. Now, the reason is because the cost of leaving that person that is positive to escape is going to be your problem. So you have to make sure at all costs you put that person under surveillance. So, but now, like I told you, there are situations where the cost is not expensive. So you like, oh, it's fine. There's not a problem. Like the malaria kit I gave you guys. And like I said, it's going to be different because when you look at somebody of European descent that do not have the gene to the protection against malaria, it's going to be a challenge. So stuff like that, you could look at it. So, but one of the setback of the precision is the fact that it ignored the false negative. It just focused on the false positive guys. And that's not how your model is supposed to do. Like we always look at the side of the coin, that it has, everything is like kind of divided into 2 sides, the positive, the negative. So when you have a model that is tilted towards or hampering more on the false positive, true positive, and ignoring the true negative and false negative, and it's not right. So you have to, use something that is able to detect both. So you could really know that this model, when I deploy it, suppose there is a change in the distribution of the data set when I put it out there, I wouldn't have problem with it. So these are some of the setback of the precision. Then coming to the case of recall, you will see that in the case of recall, it also performed well when you are talking about imbalanced classes by focusing on actual ones that your model was able to detect. So remember we talked about the spams that hit your email. 6 hit your email. 3 of them were spam mails that were detected by your algorithm. Recall will say, okay, these 3, when you match it up with the actual labels, they are actually spam mails. So because of that, you have 3/3, which is 100%. But the problem is, it's a nice thing when you have imbalance problem. You could say, oh, yes, this is how your model is doing. But again, the setback is that the recall does not account for the cause of this false positive. It just totally ignores the other 3 that were misclassified in your data set. It didn't even consider them. That's wrong. And for example, the recent judgment on in Nigeria by sorry, I have to talk about that, but I want you to understand some of those things. The recent judgment in Nigeria that the government has to declare a state of emergency in River State, you would clearly see that that was a recall issue because they ignore the other party that is causing the problem, and then they focus the whole judgment on the other party. So if you want to be fair, you have to look at the both sides. So that was a bad judgment because it's focused only on one side. So that's how the recall does. It just take care of the whole positives that comes in, the true positive, but it doesn't talk about the false positive that were also spam mails. So it has to balance the both of them for you to have a nice model. So that's where the F score comes in. The F score makes a lot of sense because it's the harmonic mean of this precision and recall. Now, consider when we talk about, of course, you know what mean means. When we talk about mean, you are averaging. So when you are averaging this two of uh, uh, matrices, you're going to be adding them up, and then talk about the total. So that's how we comes about the F1 score. So you're adding this precision, you're adding the recall. So by the time you take the LCM and all that I told you about, you're going to have the S score to be 2 times precision times recall all over the precision plus recall. So the F1 score take into account uh, the average of the precision and the recall, which makes sense because remember the recall ignore the false positive. The precision added can think about the false positive. So when you're dealing with imbalance classification problem, the F1 score is one of the ideal metrics for you to use to check if your model is actually doing great or the model is just giving you gibberish. Then it is ideal in the applications where false positive and false negatives matters. So when you are looking at a model that could take care of these issues, then the false positive is very, very important. Now you should zoom into it and try to look at it, if what your model is doing makes sense or not. Now, there is another very interesting metric that you cannot rule it out when you're talking about machine learning classification metrics scores. One of it is the ROC call or an AUC. The ROC is the receiver operating call, and then the AUC is the area under the curve. Now, when we talk about the AUC, the ROC-AUC stuff, is a plot that visualizes the true positive rate against the false positive rate. So you could see it's very, very important because these two are always like in conflict with the other. So if you want to actually know the true state of your model, you have to look at the ROC-AUC to see what you're actually guessing right, because it's measuring them at each threshold. So it means it will look at them, for example, at 10, it will look at them at 20, it will look at them at 30, 40, 50, down to 100, which most times we say 1. So it is a plot of true positive versus the false, true positive rate versus the false positive rate at different threshold. So like I said, you will see it at 10, you will see it at 20, at 30, at 40, at 60, and all that. So it's it makes a lot of sense if you could see how the model is performing at each of these thresholds. So the area of confidence are usually the areas that you are able to get correctly. So it means that anything outside here, you are not sure of it. So anything outside here, you say it's just as a result of random chance. But anything that the model is able to get, here is what you actually got correctly. But when it's also around this place here, it means your model is not doing well. So if you have a model that do completely covering all the area, it's ideal situation. That's when you're getting everything 100 over 100. But in real sense, you have to know that you don't have a perfect model. So if your model have 96, 97, okay, that's great. 90, great. 80, great. 70, great. Fine. 60, good. But anything below that, your model is struggling. Like 50, 50 means your model is not doing at all. It's not really getting anything. 55, skip, you can consider that a failure, but, stuff like that. So you have to, try to see how do you make sure that what you're getting is actually doing well. So the ROC-AUC is very, very important. Now, like I said, it is the area under curve. It measures the overall classification performance. So it is always this whole places here that you say you are very sure that is doing. Now let's look at how we could talk about these classifications using the ROC. Now, whenever you have the ROC, almost covering the entire place, and you have maybe just that's a perfect classifier. So the perfect classifier, what it means is that your model is perfectly detecting the positive and the negative class instances. So you could see, you say this is highly discriminate between them. So this is like a sort of a dream model that everybody will want. So the classifier performs better if we are able to make sure we push the algorithm to give us something like this. But sometimes in real world, you may not have this. Okay, so the ideal perfect classifier, you may not have that, but that doesn't mean you should stop to try. So you just have to keep trying. But when we talk about the good classifier, like I told you, maybe something around 60, 65, and all that is what we consider sort of somewhat discriminate, but not as good as what we have here. So we could, say the model is performing on average. That's like a C when you're looking at class performance. So you have to try to see how do you, again, push it. Then there is what we call the random classifier. The random classifier means it didn't pick anything. This is non-informative, no better than, all what it was picking was just noise. So you were not just, your model was not doing well. And even when you looked at the confusion matrix, you will be able to see if your model is, it's here, or it's here. Because what your model is able to pick from the confusion matrix will actually tell you if your model is doing the right thing or the wrong thing. So it is useful when you are evaluating binary classifiers. Although we also use it in multi-class problem, but what happens is in multi-class problem we try to pick one of the target against the other. So you do one versus rest, one versus one. So it's still going to be going with the concept of the binary, but in this case, you are now going to be evaluating them against each other. Then when you plot the ROC-AUC, you see so many curves in some cases because you are not just having one model, but we do use the ROC for multi-class problem. It's not necessarily just tied to the the binary class problem, but it is a very good metrics to tell you where you are. Now, we have been talking about this confusion matrix a lot, but we haven't really zoomed into it to know what it means on its own. So far, do we have any question? Are you all with me?
Yeah, no question from here.
Okay, great,
No
great,
question.
great. Okay, great.
Yes.
Okay.
Thank you,
So
doctor.
no problem. So the confusion matrix, like I said, is a table of representation of the classification performance that you have. So remember the true positive, the false positive, the true negative, the the false negative, the true negative. Now, excuse me. So you are going to have the predicted label, and then you have the real label. So normally the columns are the real labels, while the predicted labels are on the row. So it's a kind of cross-talking between the rows and the columns. So normally, what you normally do when you have the confusion matrix is always look at the diagonal like this. So the green part tells you the part you're getting right. The red part tells you the part you are missing out. But like I said, the model, most of the, your dream will be that you should get everything here and everything here, and this one should be, let's say, 0, 0. That's the perfect model. But again, like I said, the perfect model does not truly exist because of the random error. So you will have some errors, but what you are expected is it shouldn't be much, because when it's very few, it actually shows that your model is doing great. It shows that your model is not just detecting noise. But in a situation where you now have this red to be much more compared to the green, or even everything is here and nothing is here, nothing is here, everything is here, it means your model is not doing well at all. You have to, go back to the drawing board and see what are you doing wrong. So the ideal thing is to look at the diagonals and see if these ones are doing well. And then you can now check the offshoot and see what you are doing, what you are missing out. So you could see that the recall, like I said, is going to be what? The column. The precision is the row. Remember? So while the accuracy is everything here, so the true positive, true negative, which we have here, and then everything, the true positive, true negative, false positive, false negative, you add it up. So in the confusion matrix, you can be able to get the three classification performance matrices from them. So that's why you see the confusion matrix is very, very important. You don't just, I see a lot of people don't care about looking at it, but it's very, very important because you could actually, gauge the performance of your model, just looking at the confusion matrix. You will know what your model is capable of doing by just looking at it. Because come to think of it, the F1 score, remember, is the addition of these two, is the harmonic mean of the precision and the recall. So it means you could get the F1 score, you could also get the accuracy, you could get the precision, the recall. So you could get 4 matrix by just looking at the confusion matrix. So it really helps you to visualize the model error and also the biases that you are not able to train. And remember, we said the true positives are the ones that you correctly predicted positives. The false positives, on the other hand, are the incorrect ones that you don't get right. While the true negatives are the ones that you correctly predicted them to be negative. So if you have, like I said, when you have people that don't have cancer, the ones that have cancer, the ones you were able to predict and say they don't have cancer, and truly they don't have cancer, that's your true negative. But in the false positive, false negative are those people that do not have the disease, that you are predicting to say they do have the disease. So, like I said, each of them have their consequences. So let's look at the regression matrix overview. So the regression matrix as well is not very far from the classification matrix, although both of them are two different problems. The classification, remember we said it focused on the categories or categorical problems, while the regression focused on continuous problems. So in other words, if you are looking at such kind of issues, it means that the way and manner at which you know if you are estimating the right thing and not noise is by looking at some certain characteristics of what your fit is able to capture. So the mean absolute error is the measure of the average magnitude of error. So this is how the mean, the AME is usually represented. It's always 1 over n, then n, y, and then this is always the the target variable we're looking at that we're estimating. Now this y is going to be the cap of this other y. That's y minus y cap all over I, and if you do sampling, you'll be able to know how these things are being derived. But like I said, I wouldn't want to go into the complexity of this part. While the mean square error, it penalizes large errors. So the mean square errors is usually this one, and it should present 1 all over n minus 1. Now, excuse me. If you look at the mean, the AME and the MSE, it's looking like L1 and L2 problem. Like I'm beginning to really some of these mathematical terms are beginning to forget them. But the L1 and L2 problems are mostly when we are trying to derive some of these problems when we are looking at the lumbar lines. You discover that we're trying to shrink these errors in such a way that we would be able to minimize or optimize the problem. So, when I did real algebra, I think that was when no, functional algebra. One of it, that was when we did this a lot during my master's while I was in Kenya. So, but it's more like the MAE is an L1 issue because of this absolute. So when you are looking at them, and I wish I could be able to write. Let me see if I could get a pen. So what I mean here is that when we talk about the L1 problem, it's something like this. Then you're likely going to be having something like this, like this, like this, like this. Sorry, my stuff is not that nice. The sketch here. But remember, I'm an artist actually, so the problem is I don't draw very well with this. So it's with pencil I draw well. Anyway, so the L2 problem is something like this. Okay, so so great. So all of them are, talking about absolute. Now, because of the absolute, so it's like you knock it up here, 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 and then the other one just talk about this thing. So, but when we start going into penalization stuff, I'll tell you a lot about these things. Okay, so don't worry, I'll still see how we could talk about penalization, the lasso, and then we could look at how these things works. But we use them a lot when we're talking about like future selection. That's when this penalized model comes in. So, but in the case of the regression, so the MSE, it penalizes large errors. So most of the time we try to see how we could shrink these things so we could get some sort of optimizations. Then the RMSE is the root square of the MSE. So we just take the square root of it. So it said the square root of MSE is interpretable in original unit. Then when we talk about the R square itself, the R square on the other hand is SSR, that's the errors in the rows divided by the total sum of square errors. So you see it's going to be something like summation of I, yi minus yi cap square all over summation of I minus y bar. So the y bar talks about averaging all the errors. So we said it is the measure of the variance explained by the model. So one means it is a perfect fit. So when you looking at the R square, most of the time you'll be looking at how it's called. So it's mostly from 0 to 1. So if you are having like 0.9, that's quite nice. It actually shows that you're capturing a lot of the fit. It's what you're capturing is not noise. But when you have 0 or you have a value that is very small, closer to 0, it shows that you are not capturing the explained variances. What you're capturing, a lot of noise are more in the signals you're picking, a lot of noise are inside compared to the true values. But when you are now getting a negative value, it implies a worse performance than a simple mean predictor. So what that tells you is when you are beginning to have things like negative or very small little score, it actually have to be, sometimes it could be the data problem. You have to now go back to your data set and try to do some sort of transformation. Probably a log transform could help. And then in some cases, it means the linear model is not able to capture the complexity. So what you need to do now is to begin to look at other models, like maybe a quadratic model could actually fit the problem better, or even when maybe a log transform sort of regression model could do better. So most of the time you looked at these scores and be able to know what your model is doing, if it's actually doing it right or wrong. So we say the MAE is easy to interpret. However, it treats all the errors equal, ignoring their direction. So remember I told you is that you locked it up here, you locked it up here, you locked it up here. So it actually ignores the directionality of your errors. So, but it's very, very easy when you're looking at trying to interpret it. Then the MSE, on the other hand, penalize large errors more than the small ones because, remember you're kind of looking at how these are distributed around here. So the problem is that it is great for optimization and also interpretability. However, it is great for optimization and interpretability. Yeah, because it's easy for you to shrink them compared to. So if there is sort of flexibility compared to when we have the MAE. So, but again, the